So I'm putting this in chapter 15 because it is another K that we will be talking about, and we use it also in the lab that we do for this. But this is really found in chapter 17, page 748. So I'm going to come back to it when we do some acid-base chemistry as well. So you're going to see kind of an overlap here with this particular topic. So back when we were talking about something called solubility, we mentioned the term soluble and insoluble, miscible, immiscible. But when we said something is soluble, it dissolves. If it's insoluble, we said it formed a precipitate. But what we didn't tell you at that time was the fact that some of the precipitate does dissolve. So if we're thinking of a test tube or beaker, and here's my precipitate on the bottom, we were drawing them on the bottom, which is still going to be the case. But realize above this, you do have some of the ions from that precipitate floating above that, okay? So that is something called the Ksp, solubility product constant. Some precipitates produce a huge amount of ions, some are very small. It just depends upon that precipitate. So I have written out for you this balanced chemical equation to kind of demonstrate what we're talking about. So we have a typical precipitation reaction or double replacement, whatever you want, and I make lead 2 chloride as my solid. Well, in reality, that solid has its own equilibrium with its 2 ions, the lead 2 ion and the chloride ion. Well, because this is an equilibrium, I could write a K for it, okay? But instead, we call it a Ksp because we're talking about the solubility of that ion. So it is going to be products over reactants. There is no difference here. We're just calling it SP for solubility product. But realize that when we're talking about the dissolving of the solid, the precipitate, you never include solids in your K. So the PbCl2 should be on the bottom here, but because it's a solid, it's excluded. So your KSPs are always going to be the multiple of the 2 ions that it breaks up into. And again, you've got 2 chlorides here. So you square it like a typical K, okay? So in general, okay, your KEQ is the same as your KSP if A is ionic, and that's really all we're going to cover in our discussions. So your solid is always going to be on your left, and your aqueous ions are always going to be on your right. So that's going to be the typical way that you write a KSP equation. So vocabulary terms, just to kind of remind you of some of these things. Some calculations talk about molar solubility. It's the same as solubility. So we're talking about in water. Again, the solubility would be very different if you have a different solution, and we'll talk about that later. And this is where we get in that whole discussion before of saturated, unsaturated, supersaturated, kind of weaves in here as well, okay? So let's talk about how to do some of the simple calculations, and then we're going to come back to this a lot more extensively when we get to acid-base chemistry in chapter 17. So here is my KSP for lead 2 carbonate is 2.1 times 10 to the negative 11. So this is a constant for this particular solid. We want to find the solubility in moles per liter. So we want to know how much lead and how much, how much iron too, and carbonate I have in there. I hope I said iron. Yeah, I said lead. Anyway, so always write the solid on the left, write your equilibrium arrow, and then write your ions. So this one is nice because everything is just 1 to 1. And these are going to be aqueous, because again, we're talking about dissolving, we're talking about in water. We're not doing anything but in water at this point. So in terms of the starting point, you have none of these ions floating around in there. But then this is all 1 to 1, so this is essentially X and X. But you usually see with solubility, they write it as S's instead of X's. If you want to write an X, that's perfectly fine. But your KSP is equal to, it was given as 2.1 times 10 to the negative 11. Okay, so it's your 2 ions multiplied together. So I have S times S, so it's going to be S squared is how I find my concentrations. So this is the iron ion multiplied by the carbonate ion. Okay, so that's going to be the product of S times S. So if I take the square root of this number, my S is going to be 4.6 times 10 to the negative 6 molarity. Well, what's that the concentration of? Well, it's the concentration of the iron, and it's also the concentration of the carbonate. Well, what if it's not 1-to-1? What if it's not 1-to-1? Well, if I have a KSP of calcium fluoride, so calcium fluoride has, when it breaks up, again, write the solid on the left and your ions on the right, I have 2 fluorides. And again, both of these are aqueous. So these start at 0. This is S, and then this is 2S, because again, that is because of the stoichiometry. So this one looks a little different, okay? So KSP is equal to 2.7 times 10 to the negative 11 is equal to the calcium ions multiplied by the fluoride ions. And this is where it feels redundant a little bit, okay, just a little bit. If I were just writing the KSP expression, the K expression, I would put a 2 on the outside here. But realize that when I'm in that beaker, okay, if I was taking a look at that beaker, and I'm looking at that precipitate down there, I would have calcium ions, but I'd have twice the amount of fluoride ions in there by concentration. We've talked about this a couple different times. So this is going to be S for calcium, but this is going to be 2S. But this is going to be squared. So again, it feels like I'm doing twice the work, but it has to do with, one is the stoichiometry. So how I do my Ks is based on the balanced chemical equation. But then here, it's due to the concentration. So 2S has to do with the concentration. So this comes out to be 2S squared is 4S squared times S is 4S cubed is equal to 2.7 times 10 to the negative 11. So divide both sides by 4 and then take the cubed root. So S comes out to be about 1.9 times 10 to the negative 4th molarity. Okay, and again, molar solubility means this is going to be molarity. This is going to be molarity. So what is the concentration of calcium? Is that, but what is the concentration of the fluoride? Well, that's going to be twice that. So it's going to be 2 times 1.9 times the negative 4th. So that comes out to be 3.8 times 10 to the negative 4th molarity. Okay, so that's just an introduction to KSP. Again, it's the same as any other K, it's products over reactants, but you are talking about the dissolving or some of the ions from the precipitate. Again, the precipitate is down here on the bottom, releases and is now also in that solution. So we'll come back to this a little bit more in chapter 17 as well.